This is Mr. Martin. These are the video notes for Geometry Honors Section 10.8. We're going to be talking about the power theorems today. We're going to have three of them. We're going to prove the first two. So keep in mind, when we prove a theorem, we don't necessarily have to go through that proof again once we do it for the first time. So we're going to get our three theorems. We're just going to apply the theorems after this video to solve problems, whether they are proofs or algebraic problems. So let's go ahead and get started. We've got chords AC and BD that we can see intersect inside the circle, and we want to prove that EA times EC, so that's the two pieces of this chord AC, the product of those is equal to the product of EB times ED, which are the pieces of the other chord. So let's get our given information in there. We've got chords A, C, and BD. That's given. And then what I'm going to do is I'm going to draw in segment BC, and I'm going to draw in segment AD. So now I've got two triangles. So I'm going to draw AD and BC, and these should both be segments. And our reason for that two points determine a segment. And once we draw those in, I've got angle A and B, and I can see that those two angles intercept the same arc DC. So let me just highlight that. Here's arc DC, and I can see that angle B over here and angle A over here, they both intercept that same arc. So from that, I know that angle B is congruent to angle A if inscribed angles intercept the same arc, then they are congruent. And I can do the same thing with angles D and angle C. I could use the vertical angles, but I'm not going to use those. So I can see that angle C over here and angle D over here, they both intercept arc AB. So those two angles are going to be congruent as well. So I've got angle D congruent to angle C, and that's going to be the same reason as 3. And now that I have two pair of angles congruent in the triangles, I can say that the triangles are similar. So now I've got triangle ADE is similar to triangle BCE by angle-angle similarity, and the steps that we used were 3 and 4. So once the triangles are similar, we know that the corresponding sides have to be proportional. So I'm going to make a proportion using the corresponding sides. So I've got EA, and the side that it corresponds to on the other triangle is EB. And that ratio is going to have to be equal to ED to EC. Alright, corresponding sides of similar triangles are proportional. And then once I have this proportion, I can simply cross multiply to get what I'm trying to prove. So I've got step 7, EA times EC is equal to EB times ED. And this is just our means, extremes, products theorem. Alright, and that's it. So we started out with two chords that intersected in a circle, and we basically proved that the product of the pieces of each chord are going to be equal to each other. So now we've got a new theorem. We're going to call it the chord-chord power theorem. If two chords intersect in a circle, then the product of the measures of the parts of each chord are equal. Okay, so when you use this in a two-column proof, for two-column proofs, write chord-chord power theorem. Alright, so you don't have to write out the whole thing, just write out the name of this theorem. So it's one of our exceptions again. So that's our first power theorem. Let's move on to the next one. We're going to prove this one as well in a similar manner. So it looks like my picture here got cut off for some reason. So this is going to be point B up here. Alright, and again what we're going to do is I'm going to draw in a segment from B to C, and I'm going to draw in a segment from D to C. The triangles in this one are not quite as obvious. So if we're thinking about working backwards, I know the step right before what we want to prove is going to be a proportion. So we're going to have, and it's a mean proportion, so I'm going to have AC and AC here, and then I've got to have AB and AD in there somewhere. So I'm going to put AD over here, and I'm going to put AB over here. So if we look at AD over AC, AD, that's the short side of the little triangle, and AC is the short side of triangle ABC. Those are going to be corresponding. And then AC is the long side of the small triangle, and AB is the long side of the big triangle. So the step right before this one would be triangle ADC is similar to triangle ACB. Okay, so these are going to be our last two steps in our proof, or the second to the last and the third to the last. The proof is going to be our last step. So let's go ahead and work through this. I've got our two pieces of given information. I've got that AB is a secant segment, and I've got that AC is a tangent segment, and these are both given. And we drew in two segments, so draw CD and CB, 2 points, determine a segment. And then once I do that, we're looking for some congruent angles, and I can see in the two triangles that we're looking at, angle A is in both, so angle A is congruent to angle A, and that's our reflexive property. And here's where things get a little tricky, because I have to try and find an arc that two angles intercept. So what I'm going to do is I'm going to look at angle ADC, this angle over here, and we can see that it intercepts arc DC. And we want to look at an angle in the big triangle that also has its vertex on the circle and intercepts arc DC. Actually, I want Well, let's put that dotted line back in there. So there's that dotted line. I actually want this tangent chord angle, and I want this chord angle. So I've got angle ACD in the small triangle. It intercepts arc DC, and in the big triangle, the chord angle is angle B. Okay, so if a chord angle and a tangent chord angle intercept the same arc, then they're congruent. Alright, so that gives me this angle up here and this angle over here, and I already know that this was congruent to itself. So now we have enough to say that the two triangles are congruent. So I've got triangle ADC is similar to triangle ACB by angle similarity, and the steps that we had, our congruent angles, were steps 4 and 5. And then once we have that, we can write the proportion that we had above. So we know that AC is going to be in our means, and then we had AD and AB. Okay, and these are just the corresponding parts of the similar triangles. Corresponding sides of similar triangles are proportional. And then once we have that, again, we can cross multiply so that I get AC squared is equal to AB times AD, and this is again our means, extremes, products theorem. Okay, so again, we've proved the next theorem. This one's going to be called the tangent secant power theorem. So let's write that out in if-then form, even though you can just write this in your proofs. It says if a tangent segment and a secant segment meet at a point outside a circle, then the square of the tangent segment equals the product of the secant segment and its external, that's really important, external part. Okay, so I'm going to end this video here so you can go on to part 2 after this. We're going to look at the last power theorem and a couple of quick examples, and that will be it. Make sure you write down any questions and get help when you need it.